The next stage of glycolysis is the preparatory phase. Key things to note about the preparatory phase of glycolysis is that it consists of 5 reactions, it uses 2 ATP, and one of those ATP, the first ATP, is used to phosphorylate glucose so that it is not lost from the cell. And we also have the splitting of the carbon backbone, right? This is sugar lysis. This is the glycolysis step, and that is performed by the enzyme known as aldolase. Okay, let's look at these first 5 reactions of glycolysis. So we begin with glucose. Please learn the structure of glucose. It's showing you the ring form here. This is alpha D glucose, and alpha D glucose is the form of glucose which is able to enter onto the hexokinase enzyme, and you'll see that when we look at the mechanisms of the enzyme. This step requires ATP, and the purpose of this phosphorylation is to trap glucose in the cell. It's necessary to phosphorylate glucose to trap it within the cell, because if there's a high concentration of glucose in the cell, because we're trying to accumulate glucose in the cell, glucose is able to pass out of the cell through glucose transport proteins within the cell membrane. And we don't want to lose glucose from the cell. So hexokinase tags glucose with a phosphate. And just to kind of clarify, where you see this P in the orange circle, that is showing you this. That's what this P represents. If I draw it onto here, this is what is missing from that shorthand P notation. So it means there is a phosphate group here. So just for your understanding, this negative charge on the phosphate group is going to exclude glucose from exiting the cell any longer. So I don't know the name of the artist because I'm a lot older, than college students, but at any rate, there's a song like, if you like it, then you should have put a ring on it. Well, if the cell likes the glucose, it should put a ring on it, a phosphate on it, because that phosphate is going to keep those carbons of glucose within the cell. So that's the purpose of the first ATP, to trap glucose within the cell. And then we formed glucose 6-phosphate. Glucose 6-phosphate is acted on by an enzyme called phosphohexose isomerase. And so here you see phospho means has a phosphate. Hexose means is a 6-carbon sugar, and isomerase. Isomerases interconvert isomers, and glucose and fructose are isomers of one another. Phosphohexose isomerase is able to interconvert here the aldose of glucose 6-phosphate to the ketose of fructose 6-phosphate. So now we've got a furanose ring, and please note the form of fructose we have here is alpha D fructofuranose, right? That's the base structure, and then we have a phosphate on carbon 6. The next step is super duper important. So here we have the enzyme phosphofructokinase 1. So we have phosphofructose, so it's a fructose with a phosphate group on it. Kinase enzymes add phosphates. So phosphofructokinase adds a phosphate to fructose 6-phosphate. And we're going to form fructose 1,6-bisphosphate. Bis means two, right? Bis is referring to, this is referring to two groups which are not joined. So this is a bisphosphate because we have a phosphate here and a phosphate here, one on carbon 6, one on carbon 1, and not a diphosphate. If we had a diphosphate, di implies two groups which are joined together, so we would have a situation like that, right? That's a diphosphate. This is a bisphosphate. PFK1 enzyme, and you always must say 1, right? PFK1, phosphofructokinase 1, because we got a phosphofructokinase 2. This enzyme runs what we call the committed step of glycolysis. And the committed step of glycolysis is going to commit the carbons of glucose to flow through the rest of the glycolysis pathway. So the committed step of an enzymatic pathway is a very highly regulated step, and it commits the carbons of that metabolite to that particular metabolic pathway. So PFK1 phosphorylates fructose 6-phosphate to form fructose 1,6-bisphosphate, and we've now trapped the carbons of glucose to flow through the rest of the glycolytic pathway. Let's clear some of this stuff out because it's getting real busy and look at the next enzyme, aldolase. Aldolase, right, is going to perform the lysis step of glycolysis. And here we are breaking the carbon-carbon bond between carbon 3 and carbon 4 of fructose 1,6-bisphosphate, and we will form glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. So this is the lysis step. So if we look over here, this is glyceraldehyde 3-phosphate. So glycer, 3 carbons, 3-phosphate because there is a phosphate on carbon 3. So we have carbon 1, 2, 3. And glyceraldehyde, here's your aldehyde, right? And so we have glyceraldehyde 3-phosphate and glycerol, right? Glycerol would be this. There's your glycerol. And so, if you know the structure of glycerol and you think of the name glyceraldehyde 3-phosphate, you could figure out easily the structure of glyceraldehyde 3-phosphate. And then down here we have dihydroxyacetone phosphate. So here's your acetone, right? So we have a ketone, acetone, dihydroxy, because we have a hydroxy here, and this was a hydroxy, but we joined a phosphate group to that OH, so dihydroxyacetone phosphate, or DHAP. And DHAP is a very important intermediate as well. So please know, right, these structures. This image covers the same information that we just looked at, so we're still looking at the preparatory phase, but there's more information here on the molecular transformation of these different intermediates. And so you can see here, right, phosphorylation of glucose ensures that the pathway intermediates remain within the cell. So we commit carbons of glucose to the cell, not necessarily to glycolysis, because glucose 6-phosphate, which is easy to abbreviate as G6P, has got places to go and people to see, and glucose 6-phosphate can flow into many different metabolic pathways within the cell. So here, right, step 1, this is hexokinase, does phosphorylation of the glucose, and we end up with glucose 6-phosphate. Step 2, we have phosphohexose isomerase enzyme, which acts, and so this is essentially, it says it moves the carbonyl to carbon 2. And we need to do that so that we have a free OH group at carbon 1, which can then receive a phosphate through the action of PFK1. And now we have committed, this is the committed step, we have committed the carbons of glucose to flow through glycolysis. This next step 4 is the aldolase, or the lytic step, and we break the bond between carbon 3 and carbon 4. We end up with dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. And then we have interconversion of dihydroxyacetone phosphate to glyceraldehyde 3-phosphate by triose phosphate isomerase enzyme. And then we've got 2 molecules of glyceraldehyde 3-phosphate, which flow into the next stage of glycolysis, stage 3, which is the payoff phase. The payoff phase consists of 5 reactions, and here's the triose phosphate isomerase enzyme that I just mentioned to you. There are 4 ATP, which will be generated through the process of substrate level phosphorylation. So again, this is a minor way of making ATP. This is almost kind of like an oops, I didn't really mean to make any ATP, but I did. The point of these transformations is not to make ATP, but to transform these different glycolytic intermediates one to another. You will see that we get out not just ATP, but we will also get out energy, right? And we're conserving energy from the bonds of these glycolytic intermediates. We're conserving that energy into a usable form, and we're recapturing that energy in the form of NADH, or in some organisms, NADPH, which can then be used in other processes. Step 6 is super important. This is the only net oxidation step in glycolysis. And so this is run by glyceraldehyde 3-phosphate dehydrogenase enzyme, or G3PDH. This enzyme requires NAD plus and forms NADH, which then is able to proceed to the electron transport chain, right? That NADH can proceed to the electron transport chain. Glyceraldehyde 3-phosphate has a very interesting mechanism. It's one of the enzyme mechanisms that we will be looking at. The next enzyme in glycolysis is an interesting enzyme because this is one of the enzymes that is going to give us ATP. Now, kinases do phosphorylate things. So they add phosphates to things. And both of the enzymes in glycolysis, which give us ATP through a substrate level phosphorylation event, are both named kinases. And you know what? They're not named for the addition of a phosphate to ATP. They're actually named for the reverse reactions that you see here. So they're named for the addition of a phosphate to the glycolytic intermediate, not to ADP. So let's take them in order. Let's look at this phosphoglycerate kinase, and let's look at phosphoglycerate. Here is your phosphoglycerate, which I like to abbreviate as 3PG, 3-phosphoglycerate. Here it is. Here is, right, it's glycerol because we have 3 carbons, 1, 2, 3. The most highly oxidized carbon is always assigned priority as carbon 1. So it's glycerol because we have, right, 3 carbons, and then we have a phospho, right, on carbon 3, and then glycerate because we have a carboxylate here. The enzyme is named for the reverse reaction. So the enzyme is named phosphoglycerate kinase. The enzyme name means we're phosphorylating 3-phosphoglycerate to form 1,3-bis phosphoglycerate or 1,3-BPG. So here you have, right, carbon 1, carbon 3, 1,3-bis phospho, 2-phospho, which are not joined one to another. So this is an enzyme that gives us ATP. And of course, in the payoff phase of glycolysis, we have 2 3-carbon molecules progressing through. So everything here is doubled, and that's why you see the 2 in parentheses, because, right, and we get the 2 for these stoichiometries. Next enzyme is phosphoglycerate mutase. So we have phosphoglycerate and we're mutating it. So we again are moving the phosphate from carbon 3 to carbon 2. So warning, it's not the same phosphate. And you'll see that when we look at the enzyme mechanism. So we have to move this phosphate to carbon 2 so that we're properly set up in order to form a double bond between carbon 2 and carbon 3. In the next step, whoop, would I have a line through it? In the next step, which is performed by enolase. Here we have a carbon-carbon double bond, right? So ene in proximity to this phosphoryl group here. This is going to, the proximity of this carbon-carbon double bond is going to facilitate the offloading of this phosphate to ADP. And that is achieved through the action of pyruvate kinase. And again, pyruvate kinase, and here is your pyruvate. Pyruvate kinase is named for the addition of a phosphate to pyruvate, so we'll say it's a kinase reaction. So it's named for the addition of phosphate to pyruvate, not named for the addition of phosphate to ADP to make ATP. When we add a phosphate to pyruvate, we form phosphoenol pyruvate. So let's break down that for you. And right, so I wanted to show you the structure of pyruvate first before we cover phosphoenol pyruvate. So PEP, phosphoenol pyruvate. So here we have phosphoenol, and if you can imagine, if you replace this phosphate with a hydrogen, you would see that there's an alcohol. So phosphoenol and pyruvate, because this is the backbone, right? See the backbone here of pyruvate. We refer to pyruvate here as pyruvate in the keto form. Why? Because we have a ketone here. We also have an enol form of pyruvate, which looks exactly like phosphoenol pyruvate, except that in the enol form of pyruvate, we would have a hydrogen here and not a phosphoryl group. Here are the same reactions that we just looked at with a little bit more information regarding the enzymatic transformations of the glycolytic intermediate. Here's the overall reaction for glycolysis, and it's showing you the substrates and products. This is the net equation for glycolysis. Please know this net equation for glycolysis. Please know the names of all of the enzymes, but know especially which enzymes give us NAD+, which enzymes require inorganic phosphate, which enzymes require ADP, know which enzymes give us ATP, which enzymes give us water, which enzymes give us NADH and 2 protons released into solution. Here's a beautiful overview of glycolysis. This was prepared by Dr. Wilkinson, and if you look here, he put a fire-breathing dragon for step 6 of glycolysis, which is run by glyceraldehyde 3-phosphate dehydrogenase. Glyceraldehyde 3-phosphate dehydrogenase is the enzyme which requires inorganic phosphate and also NAD+ to provide to us NADH and to form 1,3-bisphosphoglycerate. This step is the only true oxidation step of glycolysis, so we have a net oxidation of the carbons of glucose. This carbon is oxidized. This carbon is, I'll say, it's more reduced, right? And here it becomes oxidized. So oxidation is loss of hydrogens. This is going away. Loss of electrons. And where do they go? They're being passed to NAD+ to form NADH. And this does not have a positive charge, right? It's just NADH. And it's trying to show you that NADH is also being produced in addition to the 1,3-bisphosphoglycerate. So please note the names of the different enzymes. Please note the steps where ATP is going to be required. Please note the steps where ATP is going to be liberated. So we get ATP out. Where did this phosphate come from? I think that's one of your homework questions. Where did that phosphate come from? So look back in the pathway and figure out where that phosphate came from.